Good morning, students. Today I prepared for this week that I'm going to cover the material that was given to you in the past 3 weeks because I thought from the feedback that I have received from some students that things were not well explained or clarified since they are reading it from a hand note material without hearing the voice of the teacher or just putting points on each thing that they didn't understand. They couldn't communicate with me during the lesson itself because it is a handwriting material. It is not somehow a way to discuss things 100% unless you can hear the teacher, unless you can see everything documented in front of you and everything is clarified for you face to face. I know that we can't talk face to face now because of the circumstances that we are living now, but I think that this is some way that I can approach with you, and we can by this way try to minimize the difficulties and try to get you into the material very good way, and try also to make you sure that everything is going to be seen here as you are in a class. So let me start with talking to you about what we have started from the first week of the distance learning, which was acids and bases. Now I am going to start with this topic, which was started with acids and bases. The most important things that you have to know first of all is that we have specific characteristics for acids and bases that characterize each of them in their solutions and in their behavior. First of all, if we are talking about the differences between acids and bases from the taste, we can say that it tastes, for the acids, we can say that they taste sour. While for bases, they taste, even we don't recommend or we don't ask or we don't use this way to know the taste of a base, but it is taste bitter. And I think you all know what is meant by that. So this is the first difference between acid and base. The taste of the acid is sour while the taste of the base is bitter. Then the second difference between both of them, we find that for acids, their solutions, Solution, I think you know also. Solution means when a substance is dissolved in water, the product in this case is called this substance solution. So when I say acid solution, I mean acid dissolved in water. Their solutions conduct electricity, which means that we can call them electrolytes. Electrolyte is a term used to describe any substance that once dissolved in water produces ions that conduct electricity. Again, electrolyte is a substance that when dissolved in water, it will produce ions, and these ions, they conduct electricity. So any substance dissolved in water, and because of this dissolving in water, they produce positive and negative ions, they are called electrolytes. For the third and the last time, electrolyte is any substance that when dissolved in water, you can consider this as a definition. Electrolyte is a substance that when dissolved in water, it produces positive and negative ions that are responsible for conducting electricity. What are the positive and negative ions that are produced when an acid is dissolved in water? First of all, if we describe or we use the term HA to represent any acid. If we use this one to represent any acid, for those who may ask, what do we mean by HA? HA is not an acid. It is a symbol used to represent an acid. For example, when you say Cl. So A here is the Cl. When you say HNO3, so H is this one, A is the NO3. For base, we can use, for example, BOH. There is nothing called BOH. It is either NaOH for one example. It is an example. It is not the only example. So in this case, B is Na. If you say KOH, so B here is being representing what? K. So these are general ways to represent acids and bases. If we use this general formula for the acid, we would say that if the acid is dissolved in water, water above the arrow means that it is the medium where the HA, which is the acid, is dissolved in. It will produce what? H plus A minus. These are the positive and negative ions produced in the water, and they are responsible for conducting electricity for any acid. For example, if you dissolve HCl in water, you would get H plus Cl negative. This is what we mean by the positive and negative ions that are produced in water when an acid is dissolved in it, and these ions are responsible for conducting electricity. That's why we call any acid as an electrolyte, because once it is dissolved in water, it would form positive and negative ion. The same thing is applied for the base. Their solutions conduct electricity, which means that we can call them electrolytes. Bases are electrolytes. For example, if we use the general formula for BOH, when it is dissolved in water, it would give B plus OH negative. A real example like KOH, when dissolved in water, it would give K plus OH negative. But before we go off this point, you can see that what distinguishes the solution of the acid is the presence of what? H plus, while OH is what is the representing, or what is distinguishing the solution of a base. H plus is a must within a solution of any acid, like OH is a must within the solution of any base. You can tell whether the solution is for an acid or base if you find H plus in the solution or OH negative. So one of these, if it is presented in the solution, it would tell you whether you are talking about an acid or a base. The third difference we can use here is that something called indicators. If you know regarding indicators, indicators are what? Indicators are chemicals that change color when they are moving or when they are found in acidic or basic solution. Any indicator has its own color in acidic solution, and once the solution is changed into a basic solution, the color would change. So one of the famous indicators that we use in labs is what is called litmus paper. Litmus paper has one of two colors, either red or blue. For the acid solution, it turns litmus paper blue, turns blue. Litmus paper red, while the basic solution turns red litmus paper blue. So if you want to check any solution, whether it is acid or base, you just need to use a litmus paper. If it was blue, And once you dip it in the solution, it turns red. So this solution is an acid. When it is red and dip it in a solution and turns into blue color, so this means that it is a basic solution. Another difference between acids and bases is regarding the pH value. pH is something that we are going to talk about later on. Less than 7, while pH for bases is greater than 7. pH is a measure for the acidity or the amount of H plus, the concentration of H plus within any solution. This means that for any acid, if you measure the concentration of H plus and use the formula for pH, which is pH equals minus log to the base 10 concentration of H plus. Here, if you apply this formula over the H plus in the both solutions, you would find that pH is less than 7 within a scale between 0 and 14 as a pH. You would find that any acid is less than 7 to 0. It would give you it will indicate an acidic solution. While greater than 7 to 14, it would be what? A basic solution. So how can we get this value? You should only know how much H plus is there in the solution. Apply this formula and you will find a number between 0 and 14. According to this number, you can identify the solution, whether acidic or basic. If again, it is less than 7 to 0, it is acid. Greater than 7 to 14, basic. While 7, it is considered what? Neutral solution. It is not acidic, neither basic. These are the main differences that I would like to just focus on before I go into more details about acids and bases. Second thing that I'm going to talk about now is definitions of acids and bases. Definitions means how scientists define acids and bases. How scientists define acid and bases. We will here talk about three scientists, actually three definitions. The first one is Arrhenius definition. The second is done by two scientists, actually not one, Bronsted and Lowry definition. The third definition is Lewis definition. Each of them put his own definition for acids and bases. What is acid according to each one of these three? According to Arrhenius, acid is a substance that produce H plus ions when dissolved in water. This is the definition of acid according to Arrhenius. It is any substance that produces H plus ions when dissolved in water. For example, HCl is considered Arrhenius acid. Why is that? Because once it dissolved in water, it will produce H plus. Since the substance, which is HCl, produces H plus when dissolved in water, so we can call HCl, we can say that HCl is Arrhenius acid. Again, HCl is Arrhenius acid. Why is that? Because when dissolved in water, it produces H plus. What about acid according to Bronsted and Lowry? Acid is a proton, which is, by the way, H plus. The same thing. H plus ions are called also proton. Bronsted, Lowry, two scientists, define acid as a proton donor, which means that any substance that can donate H plus from its composition to another substance within the reaction, it would be now known as an acid. For example, if you take HNO3 and react it with water, dissolve it in water by a reaction. Look at the difference here. Arrhenius didn't use water as a reactant, didn't treat with water as a reactant. He used water as a solvent. So it is always all the dissociation means breaking down. All the dissociation of acids takes place in water. So water, according to Arrhenius, is just a medium where an acid is going to be dissolved in. While, according to Bronsted-Lowry, H2O is a reactant, so it should be appearing within the reactant side of any reaction. Again, water here, what's the difference between the presence of water over the arrow and beside the substance? Over the arrow means that H2O is only a solvent. That's its only role. While it is here as a reactant. When you say it is a reactant, what happens now is that H plus would be given from HNO3 to H2O. What are the products in this case? The products H2O would become H3O plus. Where from comes the third H? It is already 2 here, and 1 comes here from HNO3. And this one comes as a positive charge, so it will give its positive charge to the whole species here, and it would be H3O plus. The remaining part here would be what? NO3 negative. In this case, we can call HNO3 Bronsted-Lowry acid. Why? Because it acts like what Bronsted-Lowry states for the acid. It donates H plus for water. Any substance that donates its H plus to any other substance, it is not supposed to be only water. Any other substance, since this one gives its H plus to water or any other substance, it would become what? An acid. For example, I could take this reaction plus F minus, or HBr plus CO3 minus 2. It would give what? H from here, it would go here. So this one becomes HCO3 negative 1. Why is that? Why is not negative 1, not negative 2 or 0? Because it is already has a charge negative 2. When it receives positive 1, the total positive 1 will eat up 1 negative charge from this one, will neutralize 1 negative charge, and remain 1 also negative charge on the product. While for this one, the remaining part would be Br minus. In this case, HBr is considered Bronsted-Lowry acid. When you are asked why HBr in this reaction is considered an acid, because it donates H plus for CO3 negative 2. Why HNO3 here? It is an acid according to Bronsted-Lowry because it donates H plus for what? H2O. What about Lewis? Lewis states that acid is a substance that can accept a pair of electrons from another substance. For example, if you took this example, NH3 plus BF3, the product would be NH3 BF3. What happens here is that N has a pair of electrons, non-bonding pair of electrons around its central atom, which is nitrogen. This pair of electrons is given to B in the BF3. That's why a bond is created here. This bond is due to the transfer of pair of electrons from the central atom, which is nitrogen, to the B here, which has a vacant orbital. You don't want to know these specific informations. Just to give you an idea about Lewis and how complicated it was, its definition. The idea here is that any substance which has a vacant orbital means like a room, a space room that is vacant, means that it has no electrons. We all know that orbitals around any element are completely or partially or none filled of electrons. So if any substance, if any element has a vacant orbital, so it can accept a pair of electrons from another substance, the whole substance is called, in this case, what? An acid. So in this case, BF3 is an Lewis acid. Why is that? If we are asked, why is BF3 considered Lewis acid? Because it accepts a pair of electrons from what? In this case, from what? From NH3. So again, look carefully that each of these definitions deals with a specific thing. In Arrhenius' case, it is only the important thing is that if the substance if the substance produce H plus in the solution or not. If it produce H plus, so it is considered an acid, just like that. For Bronsted-Lowry, it is a matter of which substance can accept or donates H plus, which is the hydrogen ion, or what is called the proton. Proton is the hydrogen ion. Any substance that can donate H plus for another substance, it is called what? An acid. So if we are asked why HNO3, HBr are considered acid, because in their reactions they donate H plus for another substance, in this case water, in this case CO3 negative 2. Why? An acid, according to Lewis, is any substance that can accept. Look the difference. Here donates, here accepts. Donates H plus acid. Accepts pair of electrons, it is considered an acid according to Lewis. One simple example is that BF3 is an acid because B, which is the boron, in the BF3 molecule, it has a vacant orbital which can accept the pair of electron, the free pair of electron, the non-bonding pair of electron from N to it. This is what happens when NH3 gives this pair of electron. The bonding between both of them is created as a covalent bond. This covalent bond is due to the sharing of both electrons here between N and B. In this case, we are not talking about NH3, we are talking about BF3. BF3, since it accepts this pair of electrons, so it is considered what? An acid according to Lewis. Let's take the base and see what's the difference in each case. Let's see how each of these scientists define the base. According to Arrhenius, base is a substance that produce OH negative hydroxide, called hydroxide, OH negative ions in water, or when dissolved in water. One example, KOH dissolved in water. Again, water is above the arrow because it is only, its only role is to dissolve the KOH. It is not reacting with it. It would give K plus OH negative. So KOH now is considered Arrhenius base. Why is that? Because it produced OH negative when it was dissolved in water. That's the answer. Why KOH is considered Arrhenius base? Because when dissolved in water, it produces OH negative. Why? According to Bronsted-Lowry, the base is an proton acceptor. Proton acceptor. Look carefully. The acid was proton donator, who donates H plus. The base is proton acceptor. For example, NH3. It was found that when it is reacting with water, it would produce, don't look at these two arrows now, it doesn't mean anything for now, just look at the reaction itself. NH3, when reacts with water, the idea is that water in this case would give what? H plus to NH3. So, according to Bronsted-Lowry, proton acceptor, which substance accepts the proton? NH3, so it is the base here. Why is that? Because it accepts H plus from water. While in this case, since we talk about acids, H2O is considered what? The acid, since it is what? It is donating H plus. According to acids, we said that the acid for Bronsted and Lowry is a proton donator. So when a substance donates H plus, it is an acid. In this case, water is the acid, while NH3, since it accepts H plus, it is what? The base. For Lewis, a substance that donates a pair of electron to another substance. Let's go back to the example that was given under Lewis definition, which was between NH3 and BF3, forming NH3 BF3. We said that what happens is that NH3 would donate this pair of electrons to the vacant orbital on B for the BF3, and because of that we can say that NH3 in this case, it is what? Lewis base. Why? Because it donates a pair of electrons to what? To which substance? To BF3. While in this case again, it is what? Lewis acid. Why? Because it accepts this pair of electrons. This is the difference in each case. I'm sorry, here I should what? Complete this reaction as NH4 plus OH negative. Why is NH4? Because it is already NH3 and it gains one H with a positive sign, so it would be NH4, the positive, and the remaining part of H2O, since don't forget, H2O is what? Is HOH. So once H is being given, the remaining part is what? OH negative. When H plus is being given to another substance, the remaining part of water would be what? OH. This is the OH. OH here is coming from what? From water. Once it gives its H plus to NH3, what remains from water is OH negative. So these are the definitions. The third point I'm going to talk about now is the conjugate acid or the conjugate base. What's the idea here? It was found that the reaction between any acid, when it gives its H plus, according to what? According to Bronsted-Lowry definition. When an acid gives its H plus, the product, or we can say the remaining part of the acid, would be called conjugate base. So we can say, in this case, acid minus H plus gives conjugate base, while any base, when accepts H plus, again according to Bronsted-Lowry, the product would be conjugate acid. So we can say that base, when accepts, so I should put adding, yeah, plus, when accepts H plus, it would give what is called conjugate acid. Let's give some examples. Suppose that we have this reaction, HCl plus H2O. According to Bronsted-Lowry, H plus H would be given from HCl to H2O. This will give what? Cl negative. It is the remaining part from HCl once it gives off its H plus H3O positive. H2O plus 1H, H3 plus 1H positive, so it would be H3O positive. According to Bronsted-Lowry definition, this is what? This is the acid, while water is the base. And according to the rule that was given before, a minute ago, any acid, once it gives its H plus, the remaining part, which is in this case Cl, it is called what? Acid, so it is the conjugate base. So these two are related to each other. The acid, once it gives its H plus, the remaining part is called conjugate base. While the base, once it accepts H plus, once you add H plus to it, it will produce what is called what in this case? Conjugate acid. So again, these two also are related to each other. We can call these pair of acid and conjugate base, while these two are called pair of base and its conjugate acid. Another example. C5 H5N plus HBr. In this case, H plus is given from the HBr acid, giving what? C5 H5 N, since it receives H plus, so it would be NH plus. N, add to it H to this side, it would become NH plus. What remains from this part is what? Br minus. So, if this a base, why is it considered a base? Because according to Bronsted-Lowry, it accepts H plus, while this one is an acid. The base, once received H plus, accepts H plus, it will produce what? Conjugate acid. For what? For the base. While the acid, once it gives the H plus, it would produce what? Conjugate base. So these are pair of conjugate acid and the base, and these are another pair of acid and its conjugate base. Look carefully that the conjugate base would be part of the acid, not something else. You should find something from the acid, the original acid, as a conjugate base. You can't, for example, think about this as a conjugate base for this acid, because nothing related here to the formula of HBr. Why? Also the same thing. The conjugate acid would be some kind similar to, with one only difference, which is the H plus to the base. So the only difference between the acid and its conjugate base, or the base and its conjugate acid, is the presence of the H plus only. Only. Just look at the H plus. And you can say, according to the rule that was given before, that if you want to find out the conjugate base for any acid, you should do only what? Take from the acid the H plus. For example, HCl. What is its conjugate base? Once you take out its H plus, it would give you Cl negative. Take, for example, HCO3 negative. It would give you what? Take this H plus, it would give you CO3 negative 2. Why is negative 2? Because the H plus was neutralizing one negative charge. Once it is removed, the other negative charge would appear. Or you can look at another way. If you add H plus here, H plus will neutralize one minus from these two negative charges, and it would give you one negative charge. So without the H plus, it would be what? Negative 2. H Br. It would be Br minus. Why? If you have the base and you add H plus to it, you would get the conjugate acid. For example, Cl negative. If I want to find the conjugate acid for it, I would add H, it would become what? HCl. S negative 2. Add one H positive to it, you would get H S negative 1. Why is negative 1? Because you add H plus. H plus will neutralize one negative charge here, and the remaining part is negative 1. So this formula is used when the question is being what? As a multiple choice question. What is the conjugate acid for something? What is the conjugate base for something? The acid, once you take out H plus from it, you would get the conjugate base. The base, when you add H plus, for example, NH3, what is its conjugate acid? Add H plus to it, it would become NH4 plus. So in each case, you are doing what? You are adding H plus. You are adding H plus. In each case, you are adding one H plus. So as you can see, the difference in composition between acid and conjugate base, or base and conjugate acid, is H plus either removed or gained. This is the third point that I want to talk about. Now, new thing to talk about is the strength of acids and bases. Strength of acid and base. Unfortunately, some students think that the strength of the acid or the base is only a matter of the concentration of the acid and the base, while actually there is no relation at all between the concentration and the strength of the acid or the base. The strength of the acid or the base is only measured by how much ionization it would go when dissolved in water. Again, how much ions the acid or the base would produce, how much molecules or units of the acid or the base would dissociate. So it is a matter of dissociation percents, the amount that would dissociate. And again, dissociate means ionize. Whenever the acid or the base ionize more, it is considered stronger than the one which is ionized less, with a less percent. For example, here, I would give you for the acids some acids to memorize, which are what? HCl, HBr, HI, HNO3, HClO4, H2SO4. What are these acids? Why do I talk about these acids? Because these acids are characterized by 100% ionization, which means that whenever you are using one of these acids in a reaction, you would find that the reaction, or let's say when you dissolve it in water, the whole amount that you start the reaction with, the whole amount, suppose that you have 1,000 molecule of this one, the 1,000 molecule would be ionized completely. No one molecule will stay as it is. It will be all the time dissociated into H plus and Br minus, and the same thing applied for any other of these acids. These are the only acids that's considered of 100% ionization. You would never find any part of the original acid in the reaction vessel or in the water without being dissociated. But what about other acids? We have many acids rather than these. Any acid that is not included in this box, it is considered weak, which means that its ionization is less than 100%. Again, which means that if you start with, for example, let me take example for a weak acid like HF and compare it with HCl. If you start with 100 molecule of HF to react with water, and here 100 molecule, what you will find finally is that the whole amount, 100 molecule of HCl, will be dissociated into what? Into H plus and Cl negative, giving 100 of this and 100 of this one. Why? HF, since it is a weak acid, you will never expect it to dissociate completely. Let's say 30, let's say, and it is an assumption, that 30% is going to be dissociated from this acid. 30% means out of 130 will be dissociated. So what we'll find at the end of the reaction, you will find that you would have H plus, you would have F minus, this one would be 30, the amount that is dissociated from here, suppose it is 30%, means that from each 100 molecule of HF, you would have 30 dissociated only, giving 30 F minus, 30 ions of H plus, but you will still have an amount of HF, which is what? 70. The remaining part which is not dissociated. While if I ask you here how much HCl you would find at the end of the reaction, it would be what? 0. Zero means that the whole amount has been completed. The whole amount has been dissociated. So this is one question that sometimes in exams you will find it. In a solution of HF, for example, or any other weak acid, suppose that we are talking about HF as an example. In a solution of HF, what substances that you would find in the solution? I would say that in the solution, I would find F minus and H plus for sure, because it would go a certain amount of dissociation. But at the same time, since it is not 100% dissociation, still some amount of HF will not be dissociated. So I can say that I would find also in the solution a specific amount of HF. Beside what? For example, the water, which is the medium that where HF is dissolved. For HCl, since it is, look carefully here, for HCl, since it is a strong acid, if I was asked what species that you would expect in the solution, I would say I would find Cl negative, I would find H plus normally because these are the ions, but I will never, don't mention anything about HCl because it is completely dissociated. And of course you would have what beside that? The water. So again, here in the solution of HF, since it is not completely dissociated, I would find F minus H plus from the part that was dissociated and the remaining part of HF plus water. 4 species, F minus H plus HF, water. Here I would find Cl negative, H plus, water with no amount of HCl. This is very important when you are talking about acid and the difference. The thing also could be said about the base. We also have strong bases and weak bases. Strong bases are LiOH, KOH, NaOH, CaOH by 2, BaOH by 2, SrOH by 2. These are the only strong bases, which mean again that we are talking about 100% ionization. The same idea is applied. Any other base here would considered what? Weak, which means partially dissociated. Look carefully about these two terms that I am using. Complete dissociation or ionization is only used for strong acids and bases. Partial dissociation or ionization is used to describe the weak acid or base. Complete ionization, partial ionization. This is the idea of the strength of acid and base. It is at all not related to the concentration of the acid and base. It is only related to how much amount. For these acids or bases that have different ratios or different percent of dissociation, if you have another acid which has 60% dissociation, it would consider stronger than HF. Again, if you have another acid which is, for example, 60% ionization, 60% means out of each 100 you will have 60 to ionize. So it would be considered stronger than the one which has 30 to ionize. Another acid which has 70% ionization would be considered stronger than both of them, the 30 and the 60. But they will all considered weak since they are not reaching what? 100%. If the acid is 100%, it is directly goes from the category of weak into the strong. And there is no acid can change its attitude from weak to strong. The weak is weak, the strong is strong. But just to put the idea or to make the idea much more closer to your minds, it is a matter of percent of dissociation. But then if this amount of dissociation increase, this means the acid becomes more stronger than the one which has lower percent of dissociation. And whenever it reaches For example, 99%. Since it is not 100% ionization, it will considered what? Weak. Once it reach 100%, it would become a strong acid. This is the idea for strong acid and bases. I think I will stop now, and in the next session, inshallah, I am going to talk about calculations of strong acids and bases and weak acid and bases. Have a good time, inshallah, and keep safe. I hope it was somehow good for you. You would find this session, you would find it on my channel on YouTube. I would send a link for you to make sure that you have it all the time whenever you want it on my channel. Don't forget to subscribe and function the the bell beside the subscription icon in order to get notified whenever I upload any new lessons on the channel of on the YouTube. My own channel, I would give you just a link for this one and for this lesson. So you would go to the link, you would go to the YouTube, subscribe and function the bell beside it so you can get notified as I told you. Thank you and keep safe, inshallah.